Now, I know what you're thinking. Your life would not be complete without revisiting the volumes of solids of revolution, right? All right, so we're going to generate the volume of a solid of revolution by rotating the following region around the x-axis, or say it does not exist if it diverges. Okay, so let's look at a picture of this on Desmos. That'll probably be better than trying to just wing it. All right, so this is that function. So it's x squared plus 1 to the negative 1/2 power, right? In other words, 1 over the square root of, I could draw it, 1 divided by the square root of x squared plus 1. Same curve, right? Okay, so if that's the curve, lovely, wonderful. And I'm going to rotate it around the x-axis, and it's bound from 2 to infinity and beyond. So it just keeps going and going and going and going and going forever. All right, but we can't draw forever, but we can draw a bit of it. All right, so we'll draw an axis. And of course, we're going to make it a nice, good axis with a nice, good picture. It's nice and large, not too crammed. We'll have some scale. This was about 10 over here. This is about 1 up here. 0, 0, etc. Okay, and then we want it from 2 to infinity. So we want to shade the line at 2. And we're going to shade to the right, right? 2 to... Actually, technically 2 is a solid line because it's got a bracket on it. But it doesn't really make any difference. So there we go. Okay, and then we're going to rotate that bad boy around the x-axis. So, oh, I don't know if I wrote that. Yeah, so around the x-axis. There you go, right there. So we're going to rotate it around the x-axis like that. Yes, you still have to draw all this stuff. There's your axis of rotation. Now, we have a choice. We can do shell method, which would be horizontal rectangles, or we can do disk method, which would be a vertical rectangle. And I'm going to use the disk method because it's easier in this particular case. Not that the shell method was that difficult, but I'd have to solve this in terms of y if I want to use shell method, and I'm not feeling it. So we will use the disk method. Because it's f of x given, the shell method would be more difficult. Shell method would require us to solve it for g of y. We would have to find this curve in terms of y. So we already have f of x. Let's see if we can use it. And we can, by the way. All right, so the shell method, or excuse me, the disk method. I just said it wrong. The disk method, let's pull out your note sheet because you don't have to memorize it. You just have to be able to use it. The disk method, see, shell method would be in terms of y. We'd be using this one. Disk method, we're using that one. That seems easy. So the volume is equal to pi integral from a to b of r of x squared. There we go. All right. Well, for us, we're going to go from 2 to infinity. So we're going to take pi integral 2 to infinity. R of x is the square root of, well, I'll just say x squared plus 1 to the negative 1/2. I'll just write it like that. And then I'm going to square that dx. Oh, I forgot my dx there. Right? So there's my function. There's my values from 2 to infinity, and so on. Now, I'm not allowed to do infinity like that, so I'm going to have to rewrite this. And I'm also going to square that negative 1/2 while I'm on the subject. So this is going to be pi, oh, times limit, sorry. I was going to put the infinity symbol first. Pi times the limit as, and again, pick your letter. I'll pick b. b goes to infinity, 2 to b, and then it'll be x squared plus 1 to the negative 1 dx. Right? So you have to do this step. You are not allowed to leave infinity in that symbol. You have to do this. Infinity is not a particular value. Right? So that means that we can rewrite this. I'm going to rewrite it as pi limit because I think it'll be obvious what you have to do next once I do this. I guess I can do it over here. It doesn't really matter where I do it. well, to keep with the verticality of my work here, I'll go this way. Let me rewrite that, because the negative power means it's 1 over. And at this point, hopefully, little bells are going off in your head. You should know what that is. It's on your integral table, but you've gotten pretty used to using that one because we use it so often in Calc 2. It's arctangent, right here. All right, so this is pi, limit b goes to infinity, of the arctangent of x. It just occurred to me, I should probably change my color here just to kind of denote that we've taken the integral here. So arctangent of x, and we're going to take that from 2 to b. All right, wonderful. So this is pi, limit b goes to infinity, of the arctangent of b minus the arctangent of 2. Okay, now I know what you're thinking. Oh, the tangent can be 2. Sure, tangent can be very large, right? Sine and cosine cannot be 2, right? But tangent is a ratio, so it can be very, very large. Indeed, it can be infinite, as a matter of fact. Okay, so I need to figure out what angle would have a tangent of infinity. So if I rewrote this, this is pi. Arctangent of 2 is just the arctangent of 2, right? This is just some constant, so we can just make a note. This part right here is constant, right? It just is what it is, right? There's some angle that has a tangent of 2, right? And then this one, arctangent of infinity. So let's think about that. So we're taking the arctangent of infinity, right? Because I have infinity in here. Oh, I better do it in pink, otherwise it'll get confusing. Minus the arctangent of 2 being the arctangent of 2. Nobody knows what it is. We'll find it. We'll find a decimal approximation at the very least. Okay, so let's think about this. Is that indeterminate? Or can we determine what that is? All right, so let's go look at arctangent for a second, which I know we have in here, but we have this Desmos graph. I'm just going to kind of turn off that graph for a second, and then I'm going to turn this on instead. So let me turn that off. Let's look at arctangent exploration here. There you go. So let me graph y equals arctangent of x. That's what it looks like. So it's slowly climbing. Wonderful, marvelous, right? Now where is it heading to? That's the question. So as I let x go to infinity, here, let me go 0 to 1,000. It's heading somewhere, right? Where is it going? See it? It's heading to 1.57. What is that? That's what it is. It's heading to pi over 2. Now, why might that be the case? Let's look at the unit circle for just a second. Let's think about this. You got your unit circle, right? Let's think about pi over 2 for a second. Pi over 2 has a sine of, or cosine of 0 and a sine of 1. So its tangent is 1 divided by 0, which we already said is not an indeterminate form. That's determinate. We know what that is. It's infinity. So that means that the arctangent of infinity is pi over 2. Nah? This right here is pi over 2. Although my pi got weird. Pi over 2. Yeah, legit, like it is. All right, so it's pi over 2 times pi minus the arctangent of 2. I mean, arctangent of 2 is just some number. Matter of fact, I can find it. That's what Desmos is good for. Oh, Desmos. Tell me what the arctangent of 2 is. There you go. It's like 1.107. And so if I want the answer, I can say that it is pi times pi divided by 2 minus arctangent of 2. So it's about 1.465. I'm curious to know what I did here. Oh, I did it already. Well, actually, let me do an integral check in here. So let me show you how I was doing that before. So I want to take the integral from, what was it, 2. I can't do infinity, so I'm going to do letter B, like that. So from 2 to b of f of x, which is my function, dx. And I'm going to add a slider for b. I'm going to let b start out at 0 and get really, really, really large, and I'll see what happens. If I let b get really, really big, will it approach the answer that I think it should be? Oh, I forgot to put a pi out in front of it. Sorry. Oh, and I also forgot to square. I'm doing a volume thing, not a here. It's this. Squared. There we go. Yep, it's the same. Look. Now, grant you, I'm losing some decimal places of accuracy here because I'm only going to 10,000, and this answer down here is going to infinity. So you can see after the 1.456, from that point on, they're a little bit different. But of course, if I let b get larger, it would be even closer. And that's a way we can sneakily check our answers with Desmos to make sure that the numerical answer we're coming up with is accurate, which it was. So I can go back here and say, hey, this is correct and this is exact. Oh, and if they gave me, oh, they didn't give me units. Pretend. I'll add this in for future. Let's let x and y be in centimeters. I'll add that in for next time. Then this, because it's a volume, would be centimeters cubed. Right? You're finding the volume of a solid. Or decimal approximation, let's get real. I mean, who would want to know that? 1.456 centimeters cubed.